Okay, so this is review part two. We'll talk about chemical reactions. So two important things we need to know in order to understand chemical reactions is that chemical reactions, just like anything else, has to obey two laws. One is the law of conservation of mass. The other one is the law of conservation of energy. What it says is um, energy or mass cannot be created or destroyed, only transformed. So in this example here of a chemical reaction, so this is coal combusting. So this is a combustion reaction. If 100 grams of coal was the beginning material, and obviously it wasn't just coal, oxygen had to be included too, right, for combustion, 100 grams of product needs to be formed. Okay, so look at over here, it barely looks like anything's in here because most of the products were gases. Okay, so that's what you need to understand. Whatever amount you add into the reaction needs to be whatever it's coming out. And then the conservation of the mass is kind of the same idea. If you put in a certain amount of energy, that amount of energy is going to be released. A lot of times the energy is stored in bonds. So a lot of the energy is a potential energy, so it's stored energy. Whereas if the energy is leaving or if the energy is being added, is usually kinetic energy, and we usually measure that by heat. Right, heat is an example of a kinetic energy. So before we proceed, we need to talk about a couple things. One is a chemical reaction is just a rearrangement of atoms. Okay, so in here, nitrogen and hydrogen are colliding together and is being arranged to form ammonia. This side of the equation is the reactant side. This side of the equation is the reactant side. Okay, and this arrow representing is a irreversible reaction, is going in one direction only. And then coefficients are the numbers in front of the molecules, and they indicate how many molecules are being reacted. Okay, don't confuse coefficients with subscripts. They mean two different things. I guess I can show you right here. So the subscript says that there are two hydrogen molecules, or three, excuse me, three hydrogen molecules. Okay, so that's what this three represents, 1, 2, 3. The subscript over here represents how many atoms are in a bond. In this case, they're bonded together. There's two hydrogens bonded together. Okay, in this case over here, you can see there is one nitrogen bonded to three hydrogens. Okay, and because of this two here, it just so happens there's two of them. Okay, so you need to be aware of that. All right, let's keep going. So in terms of energy of the reaction, energy is usually added to break bonds. And then when bonds are formed, energy is usually released. I don't want to say that happens all the time, but most of the time, this is what happens. So energy is added to break the bonds, and then energy is released once those bonds are formed. Okay, so we talked about a lot about this before, but what causes energy or what causes chemical reactions to happen? It has to be due to collisions. The greater the number of collision, the greater number of reactions. And then remember collision theory. For a chemical reaction to take place, two or more particles, right? They need to collide with the correct orientation and sufficient amount of energy. Okay. When that happens, when they collide, they create this phase in lingo phase. You can think about that way is the activation complex. And once the activation complex kind of falls apart, products are formed. Okay, so that is the process for a chemical reaction. Before we talked about the energy of chemical reactions, we do need to specify what is the system and what's the surrounding. So the system is usually the chemical equation itself, and then the surrounding is anything around the chemical equation. So for exothermic reactions, the energy leaves the system into the surroundings, whereas endothermic reactions, the surrounding energy is absorbed by the system. So it's always a relationship between system and surroundings. So now we can talk about enthalpy. So enthalpy is the amount of heat, the amount of energy that's absorbed or released during a chemical reaction, giving constant pressure. Okay, so that is how we define enthalpy. So when we try to figure out whether a reaction will occur or how much energy will come out of a reaction or how much energy is needed for a reaction to happen, what we are measuring is enthalpy. We're trying to predict enthalpy. However, enthalpy itself cannot be measured. It just can't be measured. So in reality, what we measure is the change of enthalpy. So the change of enthalpy is the enthalpy of product minus the enthalpy of reactant. Okay, so let's look at a couple cases. One is the exothermic reaction. So just to guide you here, this is potential energy, right? When we look at potential energy, we're pretty much measuring the energy in the bonds. Okay, so you have reactants here, we have products, we have the transitional state, that lingo state. Remember, for a reaction to take place, it requires activation energy for that to happen. Okay, and we know that this reaction is exothermic because energy is being released. Energy is going from the system to the surroundings. And how much energy is going from the system to the surroundings? Well, that's delta H, or enthalpy. So let me just write that down. This is how we abbreviate changing enthalpy. Okay, so this is changing enthalpy. And then let's look at the other case over here. And this is an endothermic reaction. So again, we have reactants, we have products. The potential energy for the reactants are much lower. So the amount of energy in the bond is much lower. With endothermic reactions, activation energy is a lot. So for endothermic reactions, energy goes from the system, goes from the surroundings to the system. Okay, so surroundings to the system. Okay, again, this is the enthalpy. And the enthalpy is the energy being absorbed in here during the chemical reaction. Okay, we talked about this before. Activation energy is the minimum amount of energy required for a reaction to go into the activated complex. Okay, so that's how we define activation energy. Okay, so that's how we measure energy in a reaction. So the energy is not being created or destroyed. It's just going from maybe potential energy in the bonds to leaving or entering the system. Okay. Now, there are ways to speed up or slow down the reaction. We call this reaction rates. Okay, the one thing that you need to know that as the reactants, okay, as the reactants are being consumed, so this part is being consumed, the products are being formed. So there's a relationship, as it should, right? Because if this is forming this, as this begins to be used up, this begins to be increasing, this begins to form, right? So that is what you need to know. And a formal way of saying this is the depletion of reactants and the formation of products. So depletion of reactants, formation of products. Okay, and this is concentration over time. That's usually how we measure rates. Few things that will affect rate. Temperature will affect rate. The higher the temperature, um, the more you speed up the reaction. Pressure, right? This depends on whether or not it's a gas, right? And if it's a gas, um, and then concentration. Okay, the more of reactant present, uh, the more likely a collision will occur. So all those three factors is based on increasing collisions. So all those three factors, they will affect the number of collisions that are happening, and that's how they will affect the reaction rate. That is not the case for a catalyst. A catalyst will also change the reaction rate, but will change the reaction rate by changing the activation energy, not by changing collisions. Okay. So that is the material pertaining thermochemistry, or the energy in the reactions. Um, Next, we'll be looking at acid and bases.